Hey, welcome to the Beals Science School. We're going to jump into the next big topic, which is covalent bonding and covalent compounds. We've spent a lot of time with ionic bonding and understanding atoms and how they start to fit together. And the next big step is covalent bonding. So here's what we're going to learn in this first introductory lesson. Why do atoms bond? We've covered that in ionic bonding, but we're going to get into it for the covalent bonding as well. How is a covalent bond different than an ionic bond? And what is it? And how do we know if something is held together with ionic bonds or covalent bonds? I'll show you. And what are the properties of covalent molecules? How do they act differently than the ones we've learned about with ionic compounds? And then this really important one that's going to carry us through as we start to write formulas and names, these things called diatomic molecules. So let's go. Definitions wise, so I would take notes. I'd write some of this stuff down so that you've got it. We're going to move forward. There's a whole bunch of lessons that involve covalent bonding, Lewis structures, writing formulas, all the things that are going to come up. And this is the foundation for all of that. So covalent bonding is when atoms share valence electrons to form a bond. So if we break that word up, co means together, and valent refers to the valence electrons, which are the ones on the outermost edge. So it's the sharing of valence electrons between two atoms. That makes a covalent bond. Let's go back to ionic bonding just so we can understand the difference between the two of these. In an ionic bond, we have a positive and negative ion that gets stuck together through an electrostatic force. So let's say sodium turns into a positive ion because it loses an electron, and chlorine turns into a negative ion because it gains an electron. It might have even stolen it from sodium. Now they have opposing charges. So they're attracted together by the electrostatic force, which makes an ionic bond. And so we end up with these really big things, ionic compounds that have this sort of crystal lattice structure. All right. Now, covalent bonding is different because it can build different structures. But why in the first place do atoms bond? Again, going back a little bit to our understanding of valence electrons. The thing is, and you'll hear me refer to this as an atom to make an atom happy. They're not happy or they're not sad. It's just a nice way to think about this as we're learning about chemistry. Atoms bond with each other to fill up their outermost shell. They are at their most stable form when their outermost shell is filled up. That's called the octet rule. So if we think about octet, that refers to 8, right? So atoms will gain or lose electrons, that's ionic bonding, or share electrons, that's covalent bonding, to fill up their outermost valence shell. Most atoms are stable with 8 electrons. There's 2 exceptions. Hydrogen and helium are stable with 2, and some metals will lose electrons, so they lose their outermost shell, and then the inner shell becomes the outer shell. But all of that was back in ionic bonding, where we're losing or gaining electrons. So if that part doesn't make very much sense, you might want to go check out those other lessons, because we're going to focus on the sharing part. And if we're focusing on valence electrons, then it's really important that we know how to find how many valence electrons an element has on the periodic table. The position of an element on the periodic table will tell us how many valence electrons it has. In group 1, we labeled that as group 1A. We used the Roman numeral 1. The reason we did that is that tells us how many valence electrons all of them in that group have. So hydrogen has how many valence electrons? It has 1 because it's in group 1A. The A refers to representative elements. Again, go back to our lessons on the periodic table to really understand what the A refers to. For now, we just need to know that group 1 has 1 valence electron. The next group over, 2. So 2A have 2 valence electrons. Now, I'm going to jump all the way over to the other side of the periodic table because it gets a little wild down there in the, I call this like the kind of the sea of chaos down here. So let's just go over here where things act like we would expect them to act, and then we'll deal with these ones down here in a moment. So group 3A, they have 3 valence electrons. Group 4A, 5A, 6A, 7A, and finally the noble gases have 8 valence electrons. That's why we've labeled them using Roman numerals. VIII is 8, and the A tells us that it's a representative element. So we come back here into where things get a little more challenging, all right? Now scandium and this group right here, we would expect it to have 3 valence electrons because it lives in group 3B, but it doesn't always have 3. That B is reminding us that these are transition metals or transition elements, which means their D subshell electrons can transition into other places which means they won't always have 3 valence electrons. But I'll show you how to deal with them when we get to situations where we can't use that number 3. In a lot of cases, especially in covalent bonding, if these are doing covalent bonding, then that number will hold and we'll be fine. Again, so these, we would expect them to have 8 valence electrons, but they rarely do. And oftentimes these metals are going to make ionic bonds with a non-metal way over here anyway. And then we're not going to use any of this stuff that we're learning about. We'd go all the way back to ionic bonding to deal with those. So if we do our little example here, we've got hydrogen, right? Hydrogen should have 1 valence electron because it's in group 1A. Copper way over here. Well, let's see. This was group 1A, 2A, 3B, 4, 5, 6, 7, 8, 8, 8, 1. So we would expect it to have 1 valence electron. Sometimes it doesn't, but that's okay. We can cross that bridge when we get there. Over here, potassium, how many valence electrons? 1, because it's in group 1A. Calcium, how many? 2, because it's in group 2A. Boron, 3, because it's in 3A. Aluminum, 3. And you just keep on going through here and give yourself some practice so that you can do covalent bonding. Now, how am I going to know if it's ionic or covalent? So different types of bonds will form as elements interact with each other. There are 3 types of bonds that we're going to focus on for right now. We can expand on this a little bit later and really clarify, but we're going to focus on ionic bonds, which earlier lesson, and polar covalent and nonpolar covalent. I'll get into the polar and the nonpolar part in another lesson. For now, we just need to figure out, is it covalent? Are they sharing electrons? Or is it ionic, where they've turned into an ion and got stuck together? So how do we determine this? Well, we need to go back to a lesson on electronegativity. Every element has a specific electronegativity, and the technical definition is the tendency for an atom to attract electrons to itself when it's chemically combined with another element. I don't ever use that definition in my class. I always use this one. Electronegativity is how greedy an element is for electrons. Some elements are very greedy for electrons. Some elements are not very greedy for electrons. So the electronegativity will tell us if it's greedy enough to steal electrons from another one. So this chart helps us. If we're going to predict the bond type and we want to know which one of those bond types is going to form, this is what we do. Okay, you determine the electronegativity by looking it up on the periodic table. You subtract to find the difference in their greediness or their electronegativity, and then you look at this chart. Now, there's my disclaimer down here at the bottom. This is just a reference chart to help you learn chemistry. There is no definite cutoff where something is nonpolar covalent and all of a sudden, oh, we get to 0.5 as the difference between them. It's definitely polar covalent. It's going to act completely differently because now it's polar covalent. And before it was not. Here's the thing. Think of the rainbow, right? If we have the color Roy G. Biv, red, orange, yellow, let's go from red to orange. In the rainbow, a true rainbow, where does red begin or where does red end and orange begin? Like, where is that? Is there a perfect cut? There is no perfect cut on line. It just, red gradually turns into orange. The same thing happens with these bonds, right? We have a nonpolar covalent bond. I'll show you what all of this means, but it could be it could have some slightly polar, there is no perfect cutoff. So why am I giving you numbers? Because I've found after 20 years of teaching chemistry that if I give numbers to students as they're learning this, it makes way more sense. Then as your understanding of electronegativity and bond types starts to develop, you can really kind of eliminate the numbers and you'll have a real understanding of what a nonpolar bond is or an ionic bond or anything that falls in between. So bear with me. And you can see these charts. Like if you look these charts up in a book or a reference book or online, there might be different numbers. The reason is there are no real numbers. The person teaching it to you is just choosing a cutoff point to try to help you learn the basics of chemistry. Let's go to this then. If hydrogen and oxygen combine, what type of bond will form between them? Now, how do we do this? If we go back to those quick 3 steps, we just need to look them up on the periodic table and find their electronegativity. If I look up hydrogen, I can see that hydrogen has an electronegativity of 2.20. Oxygen has an electronegativity of 3.44. Then I just subtract these to find the difference between them. And the difference I get would be a negative number, right? But there's no negative numbers. This is an absolute value. There aren't real values. We're just trying to see what's the difference in their greediness. So their difference in their greediness is 1.24. Where does this fall on the chart? Well, we can come right over here and we see that this falls within the polar covalent bond. So the type of bond that's going to hold a hydrogen and oxygen together is a polar covalent bond. I don't care about the polar part yet. I just need to know that it's a covalent bond. So now that we know that a covalent bond is going to form, we need to figure out how many valence electron hydrogen has and how many valence electrons oxygen has. We go back to that periodic table that we looked at before and we look which group they're in. And hydrogen, if you remember, has one valence electron. All right, I'm going to put one E negative here. E negative is shorthand for electron. It doesn't just have one electron necessarily. We're worried about valence electrons only, the ones on the outermost shell, because those are the ones that are going to bump into other things. Oxygen has 6 valence electrons. It is in group 6A. If I draw out the hydrogen, then there's the nucleus, and I'm showing the 1 valence electron. Oxygen over here, you can see all of the electrons for oxygen, but again, we're really only worried about the ones in the outermost shell, and there are 6 of those. If we think about this, we said earlier that hydrogen would like to have 2 valence electrons to fill up its shell, and oxygen would like to have 8. Because they have similar greediness, if they bump into each other in some sort of chemical reaction, well, then they would end up sharing. We can see that here. So our hydrogen is sharing its outermost electron with the oxygen, and they've bonded together in a covalent bond. Or we know it's a polar covalent bond, but we'll worry about that more in a little bit. Now our oxygen is not happy. It still doesn't have a filled outer ring. So if there's another hydrogen present, well, wouldn't this be convenient if that hydrogen could go and share in this location? And now look what we've done. We have just made everybody happy. Our oxygen has a full outer shell. Both of our hydrogens have an outer shell. And this compound is called H2O. This is water. And this is how water forms. When you have 2 hydrogens that just get stuck to an oxygen and they share electrons with each other. An important key term with this then is the term molecule. A molecule is 2 or more atoms held together by covalent bonds. So if you hear a reference to a molecule, you know that it's being held together by covalent bonds. There are lots of examples of molecules, and as you progress in chemistry, you'll start to see them. If you've already had some biology, you know a lot about molecules already. You just might not know the chemistry of the molecules. Carbohydrates are a big one, sugars are a big one, proteins, and I've shown several different ways that these can be drawn or represented up here on the screen. We're going to learn some of those as we progress through our lesson. Fats and DNA and all the things, and of course caffeine over here, because caffeine keep me fueled so I can make these video lessons for you. And we reach this point where it seems kind of obscure. There are these things called diatomic molecules, but I will tell you, and I tell my students this in class, diatomic molecules are going to make some of you cry. We don't want you to cry. Now, why would they make you cry? Because diatomic molecules are a special thing that you just kind of need to memorize. And if you don't memorize them and you start doing, let's say, stoichiometry, something we're going to learn down the road, and it's very complex using chemical reactions and math to solve problems. Well, one of the first steps is to write a balanced chemical equation. If you don't know what diatomic molecules are, your balanced chemical equation is going to be wrong. If the stoichiometry problem takes you 20 minutes, you get to the end and you're like, it's wrong. Well, we have to go all the way back to the beginning and realize you didn't use diatomic molecules. So what do? You have to start over. So if you can remember the diatomic molecules, it's going to save you a lot of work down the road. Well, what are they? The name kind of says it all. It's when you have 2 atoms of the same element that are covalently bonded together. Oxygen gas is an example of that. Oxygen gas, or oxygen, never just lives by itself. It's very codependent. It needs to attach to something. If there's another oxygen present, it'll attach to the oxygen. If there's something else present and not another oxygen, it'll attach to that. It just needs to attach to something. That's the diatomic part. But here's the thing. If you are reading a problem about a chemical reaction and it says oxygen, you need to remember it's not just oxygen, it's O2, because oxygen is diatomic. There are others that are diatomic, and it's really, really important. I want to look at fluorine because that's one of our other diatomics that we're going to need to memorize. If I go find fluorine on my periodic table, I can see that it's in group 7A. It's in group 7A, it has 7 valence electrons. Well, that's not happy. It's not filled up because, well, look, it doesn't have all the electrons it would like to have inside. But what if there's another fluorine around and the fluorine's like, hey, I could really what if we just shared these, like, what if we shared and we would both have 8 valence electrons, and looky there. Now it's F2. So fluorine is diatomic because if there's nothing else to attach to, it'll find another fluorine and attach to it and make F2. The diatomic elements do not exist alone. They are either bound to another one of their own kind or some other element. Here are the 7 diatomic elements that, if you were taking my chemistry class, you would need to memorize them. We have bromine, iodine, nitrogen, chlorine, hydrogen, and oxygen. And the last one, fluorine. There are 7 of them. You need to memorize them. I would write them down in your notes right now and keep track of them. If we put them together, they make a word called Brinclhof, which isn't a word. It's just fun to say. And if you can remember Brinclhof, well, then you can remember the 7 diatomic elements. Brinclhof. I don't know, I feel like I should write a children's book about the adventures of Dr. Brinclhof and how he uses chemistry to do amazing things all over but I guess that's for another day. It's so important that I actually bought the domain brinclhof.com. I did, because I feel like it's such an important word to remember for learning chemistry that if you go there, you'll see that there's nothing special going on, but I guess I'm weird, so I own it. Some people find it easier to memorize their location on the periodic table. I don't, but I'm going to show you this anyway, because this is actually one of the ways that I show my students that they can sort of keep track of these. There are 7 diatomic elements, right? And if we come over here and I sort of box them in, we end up with this, which looks like the number 7, because there are 7 diatomic elements. But we're missing one because it got plopped way over here. Hydrogen is weird. It has 1 valence electron, so it acts like these. But notice it's blue, and it should kind of live over here, but it doesn't. So those are our 7 diatomic elements. Well, let's review. In relation to the diatomic element listed, are these correct? So fluorine, if I was to have fluorine in a problem, and I'm writing out a chemical equation, and I need to write fluorine in its element form, then this is not correct, because if I read a problem, we're going to practice these in a later lesson. But if I just write F for fluorine, it's not going to work. My equation, my chemical reaction is incorrect. But if I see the word fluorine and I write F2, then yes, that is correct, because it's a diatomic element. So when I see fluorine, I'm going to write it as F2. But we have to be careful, and this is where students get confused, because I think I make people nervous about memorizing diatomic molecules, and then they're like, oh no, this isn't right because there's not a 2 there. Oh, no, hold on. Fluorine just needs to be attached to something, right? It'll either be another fluorine or something else. So is this okay? It is ionic, doesn't matter. So yes, this is okay in reference to that fluorine. It doesn't have to be F2. It just needs to be attached to something. This bromine, if we needed to write Br in a chemical reaction, this would not be correct for what we need. We should write it as Br2, because bromine is diatomic. Let's jump over here. Hydrobromic acid. Okay, well, I don't even know what that is yet. You're going to learn in a lesson coming up. But I see hydrogen and bromine. Both are diatomic. So should this be H2Br2? No, it shouldn't, because they're perfectly fine as long as they have a friend. If I need to write hydrogen, or write it in a formula, and I write H, this is going to be wrong, because hydrogen is diatomic. So it's going to go find one of its friends, and it'll become H2. Carbon tetrachloride, we've got our chlorine in here. Wait, that's a 4. Is it okay that it's a 4? Yeah, it's okay that it's a 4. It's just not going to live alone, as long as it has a friend to hang out with. Well, look at this. Hydrobromic acid has hydrogen, bromine, and oxygen. All of them are diatomic. So is it okay that they don't have a 2, all have a 2 after them? Absolutely, because they've all found a friend. And so this is acceptable. Covalent compounds and ionic compounds have different properties as well. They act very differently, and it's important to be able to recognize those differences, because, well, if you're dealing with an ionic compound versus a covalent compound in some sort of reaction, you know how they're going to act. Now, I've kind of made a mess of my page up here, but I have my students copy this into their notes, because This is kind of our foundation of making the transition from ionic to covalent, but then being able to use both of them throughout the rest of the course. So I would highly encourage you to write this down. You can add to it throughout all the other lessons. You can change the wording, but this becomes kind of like a really big help sheet for covalent and ionic bonding. I've got some more information to help you out and some things that you can use down in the description to help fill this out. Now that you have an understanding of what a covalent bond is, what a covalent compound is, we need to build on that. Like, why do we need to know that, and what can we use that for? The next step for us are Lewis dot structures, being able to diagram covalently bonded things to show larger molecules. It's a pretty big step, but I think you're going to be great at it. So watch the next video. The link will be down there, and there's stuff popping up on the screen. I do all this just to remind you to keep on learning.